Last class, we introduced SQL as a way for humans to express questions to the database. We also introduced SQL as a way to modify data and modify schemas as well. But the main thing that we're going to be focusing on for the first part of this class, for the first half of this, this term, is asking and answering questions. Cue any questions you may have had about the homework or anything up to this point. So, in the last class, we introduced this basic evaluation pipeline. You start with a SQL file. The SQL file gets transformed into a parse tree or an abstract syntax tree. We went over this last class. This is done entirely by JSQL parser for you, so you don't have to worry about this grammars and defining the translation process. You get a parsed query. We talked about what that looks like. We also talked about relational algebra expressions as a much more efficient way to represent the types of computations that SQL allows you to do, and a much more flexible way for the purposes of optimization. Now today, what we're going to talk about is how to translate from one to the other. Translating from SQL, this nice, friendly human, opinions may vary, but this nice, friendly human representation of a query into the much more simple and easy to work with relational algebra expression. So just to recap, last class, SQL, we introduced SQL, and the basic SQL query looks like this. You have a select with a target list, a from clause with a list of relations, and a where clause with a condition. And loosely put, you take all of the relations, you compute their cross product, you apply the condition, you project out the targets, and you get a result that you can present to the user. We also introduced insert into, delete from, create table, drop table, alter table. The create, drop, and alter table statements are pretty straightforward. The insert into and delete from statements we'll address in the second half of the term. So, any questions about last class? Good. So, before I can talk about translating things into relational algebra, we first need a way of representing relational algebra expressions. And so just like you have a tree representation of a SQL query, you can have a tree representation of a relational algebra expression. So I have an example up here. Projection of first officer off the, first name off the join of officers and ships on ship equals ID, specifically for the ship named Enterprise. And that is equivalent basically to this select statement up here. Give me all of the first names of officers who serve on the Enterprise. So we can take this query and just like you might take different parenthesizations of an expression and group them together into a tree structure, you can do pretty much the same thing with a relational algebra expression. You have a set of inputs that form the leaves of this tree, and each input is a relation. Every operator is a node in this tree, an inner node in this tree. So for example, the selection operator takes one input, represented as an edge down in the tree, and it produces an output, which in this case goes into the join. Questions? Okay, so now we have this way of talking about relational algebra expressions as trees. Let's talk a little bit about representation, and specifically representation in a language that you can actually manipulate these trees in. Since the class project is in Java, I'm going to use Java as an example here, but this pretty much generalizes to pretty much any language I can think of, any object-oriented language I can think of. So let's start by looking at syntax trees from the perspective of SQL. So JSQL parser defines a class hierarchy, and it uses a combination of instances and classes to create what's called a union type. And a union type basically means a collection of different classes that share some kind of behavior. So in this case, anytime you write something separated by a semicolon in SQL, that is a SQL statement. We can represent that as an interface called statement. Now, this interface doesn't actually have any meaningful methods on it, but it allows us to say that there is some object that is a statement. And a statement can be one of many different things. For example, you can have select statements, you can have create table statements, and both of those implement the statement interface. Questions on this general idea of union types? I'll be a little more specific in another slide. But before I do that, I just want to get to the core of this class hierarchy. So a select statement has a field called body that contains a select body. Now, select body is, just like statement, an interface, because it can be implemented in several different ways. So you can have a union of different selects, or you can have just a plain ununioned select statement. And both of these are classes that implement the select body interface. Now, plain select has a select list, which is a list of targets given as instances of an expression interface, has a from list, which implements, which is a list of objects that implement the from item interface, and a where clause that is, again, an object that implements the expression interface. I'm not going to get too deep into the expression interface, but a from item can either be a table-based relation, or it can be a subselect, which is a select query nested in the from clause, like we talked about last class. Any guess what interface that implements?
Subselect body?
Yeah, so subselect has a field called body, which implements the select body interface. So a little bit of a recursive definition here, but this is the majority of what you need to know about the class hierarchy. There's an expression interface which you'll be given code that essentially evaluates expressions. So as long as you follow this, you should be able to do reasonably well on checkpoint 1. Questions up to this point? All right. Now, there's one particular piece of Java syntax that I want you all to be familiar with because it doesn't come up in a lot of cases. But since Java doesn't explicitly provide a union type, a way of implementing union types, this is something that you should know. So there is an operator in Java called instance of. It takes an object on the left-hand side, and it takes a class on the right-hand side. So I can say statement instance of select, and that returns true if Java statement is an. Thank you. Okay. So you're probably, in all likelihood, going to have several different cases, several different blocks of code that look essentially like this, where you're going to test for the class that a specific object is an instance of, and then you're going to do something by casting that object to the class that you now know it is. So in this case, for example, the select statement is getting cast, if statement is a select statement, then it gets cast to a select statement, and that gets processed in some way. Okay. Any questions on anything up to this point? All right. Was it a question? All right. So the select class hierarchy was a bit of a mess. What do you think the relational algebra class hierarchy looks like?
Worse.
Worse?
Yes.
What do you mean by worse? Define worse.
A lot less organized.
A lot less organized. So let's think this through. What if I give you a so you have all of these relational operators: select, project, join, cross product, set subtraction, yada yada yada. What conceptually is can you how would you design a class hierarchy around those? What are some common features? Yeah.
They all need to have the ability to view tables.
Okay, so they all take some sort of tables or relations as input. Okay, so that suggests that I might want to have some kind of interface that represents a relation. Okay, so what can give me a relation? Or a table? A query. How do I define a query? Is a project statement a query? Or project operator a query? Is a select operator a query? Is a cross product a query? Goes on and on. Any operator that you can think of defines a table. Okay. Why don't we just create one operator interface and have everything inherit from that? Projection produces a relation as output. It has to take some input, and that input has to be given in the form of another operator. Selection produces a relation as an output. You can define it as an operator. And it takes another operator as an input. Union, same thing. Cross product, same thing. In fact, the only case that even mildly differs from this is when you have an actual relation. And, well, that's a relation. It just doesn't read anything as an input. So all of your leaves are relations. Now, you don't actually get any code for this to start off with, but this is basically what the reference implementation does, the competition, as it were. It implements a single interface operator that every single one of the relational operators implements. And then the projection operator can just read from some other operator, and it doesn't really care what that operator is as long as there's some sort of interface for producing the content of a relation. What do you think? Is this easier, simpler, more complex? Simpler. This is exactly why you want to be evaluating relational algebra. This is easy. SQL is not. I always get one group that tries to implement, that tries to evaluate SQL directly. So let me just say right now, do not do that. You will thank me or thank yourselves. Or this is one piece of extra work translating from SQL to relational algebra that will make your life so, so much easier. Okay, so we got the fundamentals, we got the basics. How do you actually do the translation? Short version, this slide. This one slide gives you everything that you need to know about translating SQL to relational algebra. I'll go into a little more depth, but basically, if you have a select statement that looks like that, you're going to end up with a relational algebra tree that looks like that. And everything basically ends up being a simplification of this. Okay. Questions up to this point? All right, maybe some will come up when I start diving into these. So let's go bottom up. Let's start with the source, the from statement, the from clause. If I have a list of relations that appear in the from clause, what's the basic SQL semantics? Compute their cross product. All right, that seems like something we can implement pretty easily. If I have r, s, t, r join s join t, or r cross s cross t cross whatever else you have. What happens if I put a select statement in there? Say instead of s, I have a select, a from nested select statement. Could you say that again? Sorry.
It starts the calculation from the innermost part.
Yeah. So if I have a nested select query, that select query is just going to define a relation. So I can just start the computation pretty much entirely from scratch. Whatever I get by translating that select query, I can just stick it in where S would go. Okay, so there's a couple of minor variations that you'll encounter. So you can have, there is a quirk in SQL where you can, or not a quirk, but there is a variation of this from clause where somebody can write r join s. Now r join s is essentially the same thing as saying r comma s, but it also allows you to say r join s on some condition. Any guesses on how that might be translated? Yeah. Yeah. So this gives you a selection predicate to apply to the output of the join. Great. R cross S, and then apply the predicate. Okay. Now, recall a couple of lectures back, I mentioned this thing called a natural join. Anyone want to remind me what that was? Yeah. Define the join of the cross product.
I don't know. That's what it said on the slides.
Okay. Yeah.
It's when any shared fields between the two schema or might naturally have one.
Yep. So it's basically shorthand, a shorthand that allows you to do an equijoin between two relations. And it's basically going to take all of the fields or all of the attributes that appear in both inputs and use those as equality join. Use those to do an equality join. So if R and S both have a field B, then it's going to be R join S on B. Well, how do you implement that? Well, same exact thing. You have a condition, the equality predicates, and you have a cross product. Now, there's a little bit of a tricky bit here because you actually need to know what the schema of R and what the schema of S are. When those are base relations, that's easy, but when they're nested queries, that gets a little bit more tricky. So in the reference implementation, there's a facility for taking an arbitrary query and computing its schema. And if you have that, this pretty much follows, this is 10 lines of code at most. Yeah?
If you run a join, you'll have two columns which should have the same values, right? It still keeps the two columns there except for where it's running, right? Like it doesn't eliminate one of the columns instead of two.
So the question is, if you have a natural join, does it eliminate both columns?
Or just one
So
column.
this is where a couple of different implementations vary. Most commercial database systems will try and keep both columns, or at least force you to explicitly say which of the two you're referring to. I think SQLite will guess correctly. There's one or two other database systems that will allow you to, that will essentially condense the schema for you. But the short answer is it depends on the implementation. Does that address your question?
Well, it was, I feel like my question was really directed more to homework.
Ah, okay. Either one is correct. Never hurts to be explicit, but either one is correct. Okay, so let's go back to our big mapping. So the source or the from clause gives you a whole tree of cross products, possibly some joins in there. Then the condition gets applied as just a selection predicate. Do I need to go into this? Basically take the selection, the where clause, and you put it verbatim into a selection predicate. Okay, if there is any aggregation going on, this is where it would go. And we'll talk about aggregation in one or two classes, depending on how time goes. But I'm going to hold off on that right now, but essentially this is where it goes in the tree. If you have a having clause, that gets applied after the aggregation. Okay, the next thing is the target clause, the target list. So this is another case where SQL has a lot of different corner cases, many of which are hard to just interpret inline, and why we like converting things to relational algebra. So the big thing here is wildcards. So if I say select star, well, this basically means I don't want to do any transformations on the data. So if I just have a select star, I can get rid of the projection. If I have select A, B, blah, 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 then I generate my target list for the projection, essentially by just taking those expressions verbatim. The tricky thing here is when I have a projection on all of the attributes that come from a particular relation. So when you're building these schemas, and when you're building the schema of your input, you need to be able to identify the origin of individual attributes or columns in the output. In other words, you need to be able to determine which columns came from R, which columns came from S. This is a place where I've seen a little bit of confusion in the implementation. So any questions? Okay. Right. So one way that you can make your life a little bit easier is to look at the column class. So column has a equals operator, a equality test defined on it, the equals method on the column class, that will respect the table names. If you have, it will say that two columns are equal if their names agree, or if either name, table is not specified or null. You can make use of that to make schema comparisons a bit easier. Okay, we'll get into that a little bit further on when I introduce project 1. Okay, so there are two operators that we haven't covered yet because we haven't gotten to lists. I'll try and get to them either later this class or next class. But if there's an order by clause, that gets applied next, and if there's a limit clause or a distinct clause, those get applied at these points as well. And finally, if you have a union with another select, well, that goes all the way at the top. And you may need another distinct operator here as well, depending on whether it's a union all or just a union. Questions? Okay, let's actually give this a shot. So do this on the board. A little more space. All right. Let's translate this mess. So where do I start?
Create table R.
Create table R? Well, let me back up. So the create table statements are there just for the purposes of showing you what the schema is. How do we translate the select statement itself? Where do we start? Yeah.
Start with S. Get the source.
Start with S. Okay. So let's go down into this lowest nested query and let's look at the from clause. Okay. So what comes after the from clause? D greater than 10. All right. Should I go back to the last slide?
Do you have to tackle the aggregate first?
So after I do the selection, or after I do the where clause, then is my aggregate. So aggregation is gamma for group by. All right, what's next?
Having the average lesson.
I have another selection. Let's use wonderful technology here.
So the aggregate is taking care of group by.
Yeah, so this is group by B, some C, average. We'll talk about aggregates next class, just so that you're familiar with what they look like. All right. Looks like we've gotten all of the points in the nested query. So what happens next? Bottom where? Okay. Wait a minute. I don't think I have r.b in this schema. I don't think I have t.c in this schema either. I'm missing something. All right, so let's look at this recursively. So I've handled the nested, I hate laser pointers. Handled that guy. But I have not handled the entire from clause yet. Missing two other relations in there. So what do I do with those? Cross product. So I've got my S, I've got R, and I've got T. All right. Now what? Someone in the back. Yeah.
Yes, F from T.
F from T. Okay, so I do want to do a projection in here. R. So I need T dot F, and then I need all of the attributes of R. All right, looks like I've handled most of this. What about this where clause? Do I need to apply that? Yes. Come on, wake up.
Yes.
Thank you. All right, so if I apply, let's say I do my where clause up here, I got a little bit of a problem. Anyone see it? Yeah.
You don't have T.C.
Yep, I've gotten rid of t.c. How do I fix this?
You got the where first.
So I'll stick my selection over here. So, oh, there you have it. Anyone a little weirded out by this? Yeah?
Do we need another selection between the cross products of R and T to know how to join them together?
R and T.
See, in the where clause, you're selecting certain attributes to join R and T on them.
Okay, well, looks like I'm joining B with the nested subquery. So, you know, maybe I want a selection predicate up here to do that. And then maybe I can make this just the t.c comparison and make this selection over here the r.b comparison. That's going to be a lot more efficient. When I get to this step, I've already filtered out a bunch of results. Also means that I can combine those two into a join. That'd be even more efficient if I can handle joins more efficiently than I can handle cross products. So right now, what I'm hoping at least a few of you are thinking is the way that this was originally phrased. Where we just have this whole chain of cross products, and then we apply the selection predicate, what I hope at least a few of you are thinking is that this is stupid. No programmer would write this code. But you know what? I'm going to emphasize this point over and over and over again. When you're doing the translation, this is what you should produce. For one very, very simple reason. This translation process from SQL to relational algebra is hard. We kind of went through it at a little bit of a blazing speed here, but there are lots and lots of corner cases. And handling those corner cases is already going to drive you insane. Don't make your life more painful by trying to optimize at this stage. And the reason for that is that one of the beautiful parts of relational algebra is that you can do optimization on it way, way more effectively when you can express the optimization in terms of a correct, let me back up. Relational algebra gives you the ability to reason about whether a certain transformation is correct. So just like what we did there, we saw that R dot B was essentially a join predicate for this cross product. And we were able to kind of make this query run a little bit faster. And I'm going to harp on this over and over again. That is something that you can automate afterwards. So don't try and, when you're doing the translation, translate from SQL to relational algebra as dumb as possible, because even that is going to be challenging to get right. Okay, any questions? All right. Good. So let's take a quick, let's say 10-minute break, or 5-minute break, and be back here, what would that be, 1:15. And we'll get to part 2. On Monday, so if you've not already formed a group or somehow gotten in touch with people to form a group with, please do that over this weekend. Yeah?
Can we use emojis in our team name?
You can try. I don't guarantee that it will work, but you can try. If you bring down the database, then you can try. You have permission to try. All right. Nothing offensive, please. But have fun. Okay. So they're not doing it. They're not in particularly great shape, but Yahoo has an exclamation mark in their name, and this causes no end of insanity for age-old, archaic, systems that have to process company names. They're not expecting exclamation marks. But I think emojis will work. So go ahead. All right. So in the last, recall the kind of overall view of the project. You're starting with a SQL query. You're getting that query automatically translated into a SQL parse tree. You're converting that into relational algebra. And then somehow, out of all of that, come query results. And so what we're going to focus on right now is that last step. How do you take the data, how do you take the relational algebra tree, and combine that all to produce actual query results? Now, there's 3 general approaches that you could take to doing this. You can do your evaluation in stages. In other words, you compute each operator in one big go. Or you could do the evaluation. You could do the evaluation one tuple at a time, and you could do this in one of two ways: either by pulling tuples out or by pushing tuples in. We're going to focus today on the first two: staged evaluation and pull. Push ends up being a bit more complicated, and we'll get to that when we talk about streaming data. So, what are these first two approaches? Well, let's take a look at this idea of staged evaluation. So I have my relational algebra tree here, and what is my goal? What am I trying to do? Just testing to see if you're awake. Apparently not. Compute the answer, yeah. So you've got a relation that you're trying to compute. What do you need in order to compute that relation? Well, you need a table, and that table is going to come from the projection operator. So in order to compute the output, you first need to evaluate the projection. Now the projection also has a dependency. It needs before you can compute the projection, you need to compute the join. If you want to compute the join, first you have to compute the selection, and if you want to compute the selection, first you need to load your table. So you conceptually go down through the tree and find a leaf. Once you reach a relation, you load it in, compute the selection on top of that, and keep going up the stack. Now for this join, you also need to first load in the officers relation, which you can do. And once you have the officers relation, you can compute fancy animations. You can compute the join of those two relations. Once you do that, you can you have the join result. You can compute the product. You can compute the projection, and then finally compute the actual output. Okay, so nothing hopefully too surprising here. This is essentially just a function call. I call give me the result on the projection. The projection calls give me the result on the join. The join calls give me the result on officers in the selection, and then selection goes to ships. And both of those load things off disk. So here's my question to you. Can we do this more effectively? Or put another way, is there anything, what are our opportunities here? What can we, how can we improve on this model? Use the pull model. Damn, figured out my clever ruse here. So the pull model reads one tuple in at a time. Why might that be better? Why would I care about reading one tuple in at a time? So I don't think computer architecture is an official requirement of this class, but show of hands, who's taken it? All right, a few people. If I say the term memory hierarchy, does that ring a bell? Show of hands? Okay, a few people. So the memory hierarchy is basically our way of saying hard disk is slow, SSDs are slightly faster but smaller, RAM is, again, much faster than an SSD, but again, much smaller, and then you have different levels of cache that are smaller, and they're progressively smaller but also progressively faster. So one of the big issues that comes up in this the staged evaluation model is that it's really, really expensive. There's lots and lots of data that you're working with in every one of these operators. The officers table could be huge, and if you have to load in 10 gigabytes of data or a petabyte of data all at once, that's not going to fit in memory. And you're not going to be able to do this staged evaluation very efficiently. Moreover, you're going to be repeatedly scanning the same set of records over and over and over again. And you want to kind of, if you can reduce the amount of memory that you're using, what's called the working set size, if you can reduce the size of the working set, the data that you're using, then everything's going to fit in cache. You're going to have to deal with a lot less computation. A lot less data being transferred between different levels of the memory hierarchy. So essentially, we want to keep the data as close to the CPU as possible in as small a cache as possible. So we'd like to, first off, minimize the working set, and we'd like to aggressively, we'd like to reuse as much computation and as much data transfer as we can. So there's this pull model that's also referred to as volcano queries or volcano evaluation. And so this works exactly in the same way, but has one major difference. Rather than computing the entire thing all in one go, you're going to compute one tuple at a time. And so the way this is going to work is you're going to start off at the very top, and you're going to want to compute the next tuple that operator, that the output is, the next tuple in the output. Now, in order to produce the next tuple of the output, I need to produce the next tuple from the projection. If I want to produce the next tuple from the projection, I need to produce the next tuple from the join. The next tuple from the join is going to mean I need to produce one tuple from selection, one tuple from ships. Ships is going to read a value in. That's going to get passed up. And essentially, the whole process is going to look very much similar to what happened in the staged evaluation. The only difference is that here, we're only going to be looking at one tuple at a time. So this kind of model where I define some sort of operator, and I say, give me the next thing. And I just keep calling, give me the next thing, give me the next thing, give me the next thing. Is that, has anyone ever encountered a similar construct in your programming language of choice? Start at the beginning, yeah? A linked list, okay. So essentially, yeah, so linked list is optimized for this kind of, is a data structure that's optimized for this type of scan. Is there, yeah? Yep. So essentially, the model that a volcano operator uses is an iterator. You give every operator the ability to essentially say when you're ready to read tuples out of it, the ability to get the next tuple, and the ability to kind of say, okay, I'm done, release the resources that you have accessed. This is basically what the reference implementation does. Every single operator is implemented as an iterator. Question? Any questions? Okay, so let's look at this case by case. If every operator is implemented as an iterator, then I need to be able to somehow define this GetNext operation for each of my operators. So let's go through some of the basics. Relation. This one should be ridiculously easy. You read one line from your input, or one row from your input. You split it into fields if necessary. You parse the data, you read it into memory and put it in into whatever structure you need, and there's your next tuple. Okay, now if I'm writing my GetNext operator like this, what's my working set size? How much memory am I going to be using over the course of calling GetNext? How many tuples do I ever need in memory? Put it that way. Yep. Just one. My working set size is tiny, which is great for cache locality. All right, let's take a look at projection. So projection has an input. It has to read something from an input operator. You can do that by calling getNext on its whatever its input is. Once it does that, figures out what the output tuple is, it's one-to-one mapping, and it returns that. What's my working set size here? How many tuples? A million, order n, 2. I only ever need the one tuple that I read in and the one tuple that I am producing as output. Again, tiny, 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 tiny working set size. It's great. All right, how about selection? It was a little bit weirder. Any thoughts? Yeah. Not the working set size, but when I do selection, how do I actually implement selection in the first place? Yeah.
You just do a binary true false.
Binary true false.
You're going to just take it one tuple at a time, and then say true or false, but it's your that's on.
Yep. So you're going to start by reading a tuple. You're going to test your whatever the condition is. And if the condition is true, great, that's your return value. Otherwise, drop the tuple on the floor and repeat the process. So in this, for selection, the distinction here is that you might potentially need to call getNext on its input more than once. Other than that, there's not much difference. Now, if I use this, how many tuples do I ever need in memory? 3? 2? So it depends on how you implement it, either 1 or 2. So I don't actually need to create a new tuple. So I could essentially just read in a tuple and return exactly the same object back to my caller if I wanted to. Okay. Union. How would I go about implementing union? Let me rephrase. Let me make that clearer. How would I go about implementing bag union? Read in 2 tuples and combine. So does union ever combine 2 tuples? Or what is the behavior of union? It takes the tuples from one box, and it takes the tuples from another box, and it puts them all into a bigger box. So I can implement that essentially by keeping track of where I am in each relation, where I'm in each iterator. I start by reading a tuple from R. If R is done, I go on to read a tuple from S. Whichever of those, that's the tuple that I return. How many tuples do I need in memory here? 1. Which 2? Which 1?
1 from R.
one from R, one from S. So do I ever need both of them in memory at the same time? So great. Again, in either case, 1 or 2, my working set size is fixed. It's constant. I love constant size working sets. Makes my life, gives that one a little bit of joy in my life. All right, cross product. This one's a little bit weirder. In fact, quite a bit weirder. Here's the messy flow chart. But what I like to do is describe this with an example. So joins or cross products can be implemented in a couple of different ways. But the most simple way of implementing a join is what's called the nested loop join, which you've just seen here. Loosely put, the idea is that you take one tuple at a time from A, and then for each tuple in A, you're going to scan all of the tuples in B, and then combine them. What's my working set size here? In terms of tuples.
So 1 plus the size of B.
Why do you say 1 plus the size of B? Why do you say that?
Just for the one A that you're holding.
Okay, so I've got the one tuple from A that I'm holding. Why do you say the size of B?
Because you're iterating through all of the different. Well, I guess you can just
That is a great observation. You can do both, actually. So there are two approaches here. One where you keep one tuple at a time from A and one tuple at a time from B, which a working set size of 2 or possibly 3, depending on how you call whether you need to construct an output tuple. But the observation there is that this means that you need to keep recomputing or reloading or keep pulling things in from B over and over and over again. And that's going to be way, 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 way slow. So your instinct there is perfectly on. What ideally you'd like to do is load in all of the records from B, scan those in once, and once you have those in memory, you can just keep what's called materializing all of the tuples from B. And once you have those, you just keep scanning over and over what you've already materialized. Anyone see the downside? Too many tuples. This is there's no bound on the number of tuples that you could get out of B, so there's a potential that you're going to run out of cache space, and you're going to have to go into memory, or worse still, if you have to take all of these tuples and put them on disk. Yeah? Paginate. What do you mean by paginate?
Start with the first 100 tuples of B, join those to A, and then move on to the next 100, and then the next 100.
Okay, so you start with a bunch of tuples of A and a bunch of tuples of B, and make sure that you pick these numbers so that they fit in memory. That's a great idea. In fact, there's a name for this. This is called block nested loop join. So loosely put, the idea is that you take your two relations and you split them up into blocks. Once you have each of these blocks, you load those blocks into memory, and then you do a nested loop join on each pair of blocks. Because all of them, because they're already in memory, you're pretty much you can do nested loop join if. All right. Any questions? All right. So that is actually all I have for you today. And we will resume on Monday with extended relational algebra.